Hi, good morning, everyone. I'm Rebecca Wright, Chair of Computer Science at Barnard. We are here for our computer science seminar today, and we're very excited to have Dr. Eysa Lee with us from Brown University, where she is a postdoctoral research associate in the Data Science Institute. Her research focuses on practical cryptographic protocols, especially digital credentials, signature schemes, and multi-party computation. She earned her PhD from Northeastern University and did her undergraduate studies at the University of Texas at Austin, and she'll be telling us today about her work. So the floor is yours.
Thank you, Rebecca. And thank you everyone who came in person, online, and who may be coming from the future. Watching the recording. So I'm going to be, my name is Eysa Lee. As Rebecca said, I'm a postdoc at Brown, and today I'll be telling you about digital authentication, distributed and anonymous. So first off, let's go over what is digital authentication? What does that even mean? So let's say that we have Alice and Bob, and Alice recently saw the Super Bowl, and she's like, wow, Kendrick Lamar, that guy is great. And so she wants to tell her friend Bob that Kendrick Lamar is the best. But partway through trying to send this message over to Bob, her message gets intercepted by some adversary named Eve, who decides to go and yoink that message and instead changes it to saying that Drake is the best. Well, at its core, cryptography sort of solves this problem of secure communication by ensuring both privacy and authenticity. So what we mean by privacy is that an adversary who intercepts Alice's message can't get anything meaningful from this message. And if she tries to send a message on Alice's behalf, Bob can identify that this is not the intended message. Nice try. This talk is going to focus on authenticity, which is being able to identify that something is not the intended message. The way that we can guarantee authenticity, or we can ensure this, is through digital signatures, which is essentially the digital version of, like, think of a handwriting signature. It's something that we can attach to a message, it's verifiable by Bob, and he can be confident that whatever this thing is attached to is authorized by Alice. This is a message that she intended to send. And I'm going to use little drawings, but these are actually in reality very, very large numbers. Here's, just a bunch of things that I'm not going to read. The way that she can generate this signature is through the use of some secret information, which we're going to call a secret key. And again, the secret key is going to be some very, very large number. And digital signatures are very useful for more than just telling people that you love Kendrick Lamar. It's also useful for if you have a Git commit and you want to sign in and say that, hey, this is actually the change that I want to put in my code. I can produce a signature. For example, like if we want to look at the signature I did for, one of my commits, we can do like, you can see I have a little signature to verify that this is the actual change that I made. And if anyone wants to, they could go to my little GitHub page and say, hey, look, this was actually, signed and pushed by Eysa. And it's a picture of me with my rabbit. But anyways, it's a paint drawing. But you can understand kind of that these keys are very valuable. This is what allows us to produce this certification that a message was what we wanted to send. But you can imagine now that, like, if I store this on a single device on my computer and something happens to this computer, it gets compromised by an adversary, well, this adversary can do all sorts of things on my behalf. And, your cryptography can't save you because they generated this honestly, they have the secret value. And so with my GitHub example, an adversary can easily push some malicious code. Maybe, you have some vulnerability that people can't tell that, like, I've introduced a vulnerability into your code. Or if you're using signing for cryptocurrencies, concretely, she can steal money. Or if you're using DNS, I can even just, you want to know what the IP address for Google is? Well, I'm going to tell you it's something that I control. And so you can understand that this is a very, very high value, kind of, you need to protect your secret keys. And so how do we solve this? a natural solution, like a natural way of solving this is we can try to distribute it. And instead of having this single point of failure, we require an adversary to compromise multiple devices in order to do this. So another goal that we might have is that, well, these keys are really valuable. We have all this existing infrastructure. We have all these things in place, and maybe it's kind of hard to get GitHub to like introduce something new. So can we have a solution that is compatible with what's already in use, will already, the same thing. GitHub doesn't have to change its underlying, infrastructure that much. And so the way that threshold cryptography works in this context is that instead of this single computer, I'm going to split my key into multiple pieces and distribute this among multiple devices. And a key thing about distributing this key, notice how they have little fractions, different little fractions, is that at no point should we reconstruct this key onto a single device. Because see, if we take all these components and we put it back on a secret device, then an adversary can either just wait to, just sit on that device, wait for it to reconstruct, and then get a hold of it. And this kind of defeats the entire purpose. So instead, what we need is that we need these devices to compute the output without reconstructing this secret. So they need to have some way of doing this where these secret components never come into one device. And typically, you have like a T out of N thing where T is like some number of devices that have to come together to produce this output, and N is the total number of things. And so maybe in this case we have 2. And so it's my computer and my laptop, sorry, my phone and my laptop, maybe they can talk, or maybe I got my 2 computers to talk to each other, or maybe I just choose my other computer with my phone. And at the end of the day, after they do all of these things, they should be able to produce an output that is interchangeable, like looks the exact same as if we had done it with the original secret key. Cool. And so that thing that I was talking about before about like the T of N, we call that the threshold. The value T is a threshold. And so we're saying that an adversary cannot produce a signature without corrupting enough devices. So without corrupting some threshold number of devices. If the adversary only corrupts this single computer right here, they can't produce an output. And this even includes an adversary who kind of like sits around on this computer and can fully control it. Maybe she's waiting to strike. She still should not be able to produce an output, even if she's like, actively contributing into things. And so that is kind of the overview of my research. A lot of the research through my PhD has been on threshold cryptography, distributing these protocols. I've highlighted it in blue, and my research has also spanned through anonymous credentials more recently, and very, very recently, more foundational questions of modeling security. Broadly, my work is in 3 categories of efficient protocols, some applications, and foundations. But this is, kind of a lot to try to fit into an hour. So the focus of this talk is mostly going to be on. Sorry. I'm just very excited. So you missed the beginning where we got to talk about Kendrick Lamar.
What?
Kendrick Lamar.
Hey,
It's okay.
I saw him.
Live?
No,
Oh.
just watching the Super Bowls at the field. Never did.
But yeah, so this talk is going to focus on my works on threshold ECDSA. This is the kind of some works from my PhD, and then near the end we're going to touch on some applications with anonymous credentials. So, what is ECDSA? Well, it's the elliptic curve digital signature algorithm, and it's a standardized signature scheme, standardized by NIST, and it's used all across the internet, just everywhere. That's really cool. So why do we care about this? What's the problem? Well, this algorithm is actually kind of non-trivial to distribute. And you might think, well, why don't we just use something that's easier to distribute? Well, unfortunately, we're stuck with it. It's very common for governments and institutions to only allow the use of standardized scheme. And we have this issue of legacy code and backwards compatibility. And it's really hard to get people to change things that are already being used. So,
What
Yes.
do you mean non-trivial to distribute? Like why or what does it mean?
Oh, sorry. It means that it's not like super straightforward to distribute. Like we actually, this is sort of like a why is this even a research question? Like why is this something that I've worked on in my PhD?
Is anything distribute?
Uh,
Yes, I don't know how to judge. How do you judge if something's easy or hard to distribute?
Yeah, so for example, the Schnorr signature scheme is pretty straightforward to distribute. There are like kind of issues with like how you do it, but there's some things that like lend themselves to distribute.
To distribute and clean them.
Yeah.
Okay, good. I thought like ship some keys or something. Now I understand distribute as in distributed computation.
Yes, distribute, yeah.
Sorry.
No, no, it's okay.
I was late. Yes, sorry, I got it, yeah.
It's totally fine. Yeah, so we have this problem of legacy code, and this is used in a ton of places. So obviously, if we want to protect these keys, we want to use things that are actually used in practice. And so my work's on threshold ECDSA, same group of authors. I love them a lot. My works. So prior to my first work, the state-of-the-art required 4 rounds to produce a signature. And it was kind of a little bit of time. And so our work outperformed this best prior work by a factor of 11 for producing a signature. I'll give kind of more context for how long this is, but it's just worth noting that in the years since, there's been an explosion of work. This is not everything. This is not like an exhaustive list, and there's not nearly enough time to talk about everything that's been going on with threshold ECDSA. So this talk is going to focus on my most recent work, DKLS 24, which is titled Threshold ECDSA in 3 rounds. And as we put in the title, this is the fewest rounds. This requires 3 rounds, which is the fewest rounds of interaction for this line of work. And it's concretely efficient. For 2 parties, it only takes 4 milliseconds to produce a signature. For 64 parties, 500-ish milliseconds. And for context, the state-of-the-art prior work requires nearly 2,500 for 2 parties. So you can see that this is a very concretely efficient protocol. And the nice thing is that it's actually very conceptually simple. And so it's simple enough that I can explain the high-level ideas in this talk. And something really neat with this threshold ECDSA is that through the years, I've actually gotten to see my works out in the wild, deployed in the wild. And these are only the implementations that we know of, because especially for these proprietary implementations, either they tell us or they publish it somewhere online. Some of these older ones are going to be have been since deprecated because at this point they're a little bit old and a bit subsumed by this 24. But yeah. Threshold ECDSA has gotten to the point where NIST is even looking at standardizing threshold ECDSA, and we were invited to throw our hats into the ring and see where that goes. So it's a very exciting time for threshold ECDSA. Now, this part of the talk is going to require a little bit of math. So I'm going to go over just the basics of the notations that we're going to be using. We're going to be working over a group, this fancy G, which just a helpful abstraction so we don't have to deal with like actual numbers. And we're going to let this lowercase g be a generator, which basically means that any element in this group can be written in terms of like this g to the x, where x is known as the discrete logarithm of g to the x. And we're going to let this letter q be the group order. Order meaning the number of elements in a group. And in our context, this is going to be a very large prime. And multiplication is going to be the operator in this group. And it's just worth noting that when you multiply 2 group elements together in the exponent, you can add them. And so that's just kind of like a helpful relation to know. And the discrete logarithm assumption at a very informal level is going from x to g to the x. Very easy. We can do it. Great. But trying to go from g to the x to x is hard. Boo. We don't want to wait for that. That's way too long. Okay, cool. This is our notation. So let's look at the signing algorithm. And I'm going to just give a big disclaimer warning that this algorithm's a little bit ugly. And it's okay if you look at it and you're just like, I don't know why it looks like that. You can blame NIST for us being stuck with it. And through looking at this algorithm, we'll understand why it's kind of hard. So First, we have as input a secret key, which we're going to call SK, and it's going to correspond to some public key of the form G to the secret key, and we're going to have some message that we want to sign. First thing we're going to do is we're going to sample some fresh randomness from ZQ, which ZQ is just the integers mod Q, so think of 0, 1, 2, up until Q minus 1, because Q is a very, very large prime. Then we're going to compute this G to the K. And then we're going to compute hash on the message. And so hash functions actually, have some other definition, but for our purposes, you can just think of this as we're mapping a message to a ZQ element. So we're just mapping this to like a different value. And then we're going to compute this S value, which is our hash of the message, plus secret key times Rx, where Rx is some value that is dependent on R. But for our purposes, just think of it as a constant. Once we set this R value, once we compute this R value, Rx is a public constant. And then we're going to divide all of this by K, our secret nonce. And we take as our output this S and R. And so you might have noticed there's a little bit of color coding going on here, where blue is secret values, purples are outputs based on a secret value, and black is some public constant.
And what is X? I need to know what X is.
So this is there, so like Rx, like that's just basically because like this R is like a elliptic curve point, so it has like an X component and a Y component. And so
Oh, I
it's,
see.
yeah. Okay, so how do we make this threshold? Well, recall our original goal, which is that we want to distribute this key. We want to, make it so that we can just do this computation distributed. So that means that the first step that we need to do is we need to take these secret values and then we need to distribute them. And this is going to require some more math. We can use something that's known as additive secret sharing, which is essentially, we have a secret value, and for the ease of explanation, I'm going to have just Alice and Bob. These techniques actually generalize pretty easily to more parties, but it's harder to fit more people on the screen. So just Alice and Bob. If we want to share a secret value, what we can do is we can choose two values, XA and XB, that sum to this value X, and then give each party this value. And so this bracket notation is going to indicate that this value is shared in this way. Now, why does this work? Why is this secure? Well, you can consider an adversary who only has XA. She knows nothing about the other's value unless she knows the secret value. So if her value is like 5, she doesn't know what the secret value could be because Bob's value could be literally anything. So that's kind of the general intuition behind additive secret sharing. So if we use this to share our values, it's useful if we're able to perform computations on them. So let's look at how to do basic computations. Well, if we have two secret values that are shared, X and Y, and we want to compute shares of, we perform operations. Well, X plus Y, these values, you can see if we just locally add our two shares together, we can get shares of the sum. Now, if we want to multiply by a constant value, each party can just multiply their share with this public constant value. And if we want to sum with a public constant, we just choose one party who adds this to their share and the other party keeps theirs the same. Cool, simple. It's very nice. But what if we want to multiply values? Well, this gets a little bit trickier. And so let's take, this product, X times Y, and write out in terms of these shares what this would look like. So we have our shares, A and B. And if we write out, expand this out, then notice that we can put these terms in terms of which parties hold each value. So these first two, notice that these are both shares that either Alice knows both values or Bob knows both values. So Alice and Bob can locally compute these two on their own. But in order to compute these second two terms, there's going to, it's going to require some sort of interaction, some sort of way that Alice and Bob multiply these two secret values together. And in the context of this talk, there's many, many ways of doing this. In our work, we give a very efficient way of doing this. So I'm just going to abstract out this entire computation as just a little magic multiplication box that takes in these shares. It requires some interaction to compute this product, but it's going to output shares of these values. And so yeah, we're going to have that little box there. And now that we know how to distribute secret values, we can apply this to our algorithm. So shares of the secret key we can generate when we generate the public key, and shares of this K value, each party can actually just locally sample their own value of K, and it's going to sum up to a value that's secret, not known by anybody. So I'm going to replace all of these secret values with these little bracket notations. Cool. Now that we've shared the values, let's go on to the next step, which is actually computing the output without revealing these secret values. So let's zoom in on this S that's kind of tricky. And let's think about, how do we compute this? Well, we already know how to do this top part because I've showed you how to add and multiply public constants. But what about this inverse? How do we compute the inverse of an additive secret share? Well, if we look at it like this, okay, I have shares of X. We can't do the thing with multiplication where we wrote it out in terms of like these shares. So it requires a little bit more care. And there's a really cool technique by Barnard and Beaver from the 80s where suppose parties have an extra random value. We're going to call it phi. Well, we can take this 1 over x and rewrite this in terms of this phi value, add the top and multiply the top and bottom by phi over phi, right? And notice if we rewrite in this way, then this problem turns into secure multiplication. If we can compute this x times phi, we can invert it in the clear. And so we don't have to invert this as secret shares. And it's okay to reveal x times phi in the clear as long as nobody knows phi, because this phi, similar to additive secret sharing, hides this x, masks this x. And so we've already seen how to do the secure multiplication. We give a efficient protocol to do that. And so this is kind of a nice way to do this inversion. And so we can take this and apply it to our ECDSA signing algorithm. We have our picture from before. Now we add in sampling this random masking value, phi, and then multiplying it and expanding it out. This is the rewriting of our equation. So let's look at how to turn this into a protocol. Wink. We have Alice and Bob again, and they have their shares of the secret key from the key generation. Well, first thing they're going to do is sample these random values locally. Easy. The next thing they need to do is establish this R value, establish the shared key. And then, so this public value, I'm going to skip it because they can do that H of M on their own locally. Next thing they need to do is compute the product of these two shared values in this S, so they can run a multiplier together. They also need to compute the product of this K and phi, run a second multiplier. And then they need to, in order to do this inversion, remember you want to reveal this bottom value, so they reveal K times phi, and then they can also reveal this top part. And it's okay to reveal this top part because like you're outputting, this fraction anyway, so like you have to compute it. And cool. So this is like the general outline of what our protocol looks like. But of course, we want security. We want to be able to, protect against an adversary who can misbehave arbitrarily. So what can an adversary do? Well, first, it could influence this R so that it knows this K value. It could also try to use bad inputs into this multiplier. So it could try to use a share of the secret key that doesn't correspond to the public key. Or notice that this phi value is used in both multipliers. Maybe it uses inconsistent phi's. And maybe she tries to use a share K that doesn't correspond to R. And finally, she could try to reveal incorrect values. So these three, influencing R, different phi's, and revealing incorrect values, those are kind of like standard, a little bit easier things. So we're not going to talk about how to do them. The interesting question in here is actually how to make sure that her share of the secret value, she's using the right share of the secret value, using the right share of this K value. And yeah, so making sure that she's using these correct values. So a lot of the prior works, in order to kind of enforce this consistency, enforce that, Alice is using these correct values, would use heavy cryptographic machinery like zero knowledge proofs, which add a lot of computation time, or maybe possibly add rounds. And something that we used in our work is that we constructed a very lightweight check based off of these phi values, kind of treating them as a message authentication code. And so I'm going to go over the brief high level of how this works, how our check works. But I want to give another disclaimer that due to time constraints and due to time constraints, I'm not going to give the exact check. There's going to be some things that you're like, but how do you do that? Because more detail would require actually going into the details of this multiplying box, which we don't have time for. So the high level idea is let's look at this SK. Remember that we want our SK to be corresponding to our public key. So notice that if we take this relation and we exponentiate both sides by this phi value, then G to the SK times phi, that is what we're trying to compute shares of in our first multiplier, right? And so if we rewrite this in terms of the shares that we're trying to compute, and we move things around, well, we can write this in terms of either public values and shares that Alice has, shares that Bob has. Ignore for a second that they shouldn't know what this phi value is. Let's suppose there's some way that, Bob can get this PK over phi. And so what we can do is we can have Alice send this G to her, her share of the output over to Bob. Bob computes his side, and they compare whether or not these two things match. And so that's the high level idea. And I put a little asterisk here to remind you that this is not exactly what happens, because you might notice it's not symmetric. We're not going to break the abstraction though. And some fun little tidbits about this is that this check is information theoretic. We don't rely on any computational assumptions, and it uses intermediate values that we already have to compute because we're trying to do this inversion. And this same idea applies for checking this K times phi, but we're going to use R instead of the public key. And this lightweight check has been a theme through all of my line of specialty CDSAs. And so that's kind of the general idea. This is sort of, we add in this little check, and now we only reveal the output if the check passes. And I promised you 3 rounds, so notice that we can do a lot of things in parallel. And if we order it like this, boom, 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 3 rounds. And our techniques generalize for more than 2 parties. And so that is specialty CDSA in 3 rounds.
When you say more than 2 parties, is it like point-to-point communication?
Yeah, point to point. Cool, and so now we've kind of gone over how specialty CDSA works. So let's look at anonymous credentials. And in order to understand how this works, let's look at just normal credentials, normal verifiable credentials, the digital version of something like a driver's license or a passport. Typically, it relies on some, you have some authority figure. I'm going to use an example of Brown. Brown says sup, who holds some sort of secret key. The credential would be issued by, I take a bunch of attributes like my name, my job. Brown has an on-campus bar, so maybe it says whether or not I can drink because I'm over 21, it says my office, and it produces a signature on all these different attributes. And then it gives it to Alice. And so when Alice wants to use her credential, she can go to Bob, the verifier, and say, hey, here's my credentials issued by Brown. And if Bob trusts Brown, then goes, okay, cool, yeah, I trust Brown, sign this thing, and so I believe you. However, what about privacy? What if Alice goes to another person, Carol uses her credential? Well, there's nothing that stops these two from talking to each other. There's nothing that stops these verifiers from pulling information about you, your attributes, your usages. And if you think about your driver's license, any physical credential that you own, it has a lot of information about you. It has your birthday, it has your address, has, things that maybe aren't fully necessary for what is needed for this task. And And so there's nothing stopping these guys from just collecting data on you. In recent history, we've already seen the potential for misuse with wide-scale data collection, Cambridge Analytica. And this idea of using digital IDs is actually kind of already being talked about. There's articles 2025, there's a Supreme course about Texas wanting to require age verification in order to access adult content. And so we can already see that it's like maybe a little on the horizon. And so it really matters that the way that we do this in a way that preserves privacy. And the natural solution for this would be anonymous credentials. This is the privacy-preserving variant of verifiable credentials, which allows the user to obtain and use this credential without revealing their identity or the credential itself. And so we're going to have a similar paradigm as before, which is you have your signature same, but instead of just outright giving the credential to the verifier, I'm going to use a zero knowledge proof to show, to prove possession that I have this credential. And so some important properties with this is unlinkability, which means that these verifiers can't tell that they saw the same credential, and they can't even tell that it's the same person who was using their credentials. And so you can't link different usages, you can't track people. And something else very desirable is select.
And the same person goes to the same service twice, or these two should be linkable?
They should not be linkable. Even if I am I have one credential, I keep using it with the same person, they shouldn't be able to tell that it's me with my one credential. And it's also very popular for this support selective disclosure, which is maybe there's some relevant information, like I want to drink and I need to state that I'm over 21, I want to access adult materials, I need to state that I'm over 18 or whatever age you need to be. And so that is also a desirable property. And speaking of,
I want to understand, if you're over 21, you're saying that single thing that says your age could be used in one place to prove you're over 21 and could be used in another place to prove you're over 18.
yes,
Or it's not that you have two credentials and
No,
sometimes
no.
you show this and sometimes you show that.
You can do either, you can reveal it in the clear, or maybe you have some attribute that's, one attribute says over 21, one attribute says over 18, or
You
maybe,
need in advance to know which attribute you want to prove.
yeah,
Like
yes.
if I come up with a new thing that you need to be over 20, then you would have to reveal you're actually over 21.
So you can support predicates on these zero knowledge proofs. I think that wouldn't be necessarily selective disclosure, because selective disclosure, you're saying here's the exact attribute,
Yeah.
but you can also in your zero knowledge proof, just add in a little predicate.
Yeah, thank you.
Yeah, no, of course, if anyone else has questions. But yeah, so these digital credentials being on the horizon and privacy concerns, the EU actually recently had a regulation back in 2024 wanting to have a European digital identity wallet within the next 24 months, which by their timeline would be 2026. And something kind of interesting and cool with this is that they do have in this regulation privacy baked into it. They're saying that you should not be able to collect information about how this wallet is used. You shouldn't be able to combine data from other places to get things about these people. And you should not be able to track, link, or correlate usages. And they even try to say unlinkability. They spelled it wrong, so it's unlikability, which it's very easy to be unlikable, but but they mean unlinkability. And so something kind of cool with having these privacy preserving guarantees in the regulation is that the European Commission actually solicited feedback from subject area experts just all over, including cryptographers. And so I was part of the group of cryptographers who jointly authored a response to give feedback on their proposed design. That's me. It's a little large group of us back in 2024. And we argued that what they proposed, the architectural reference framework, doesn't actually meet the regulation requirements. It doesn't actually meet these privacy requirements. And we argued that hey, you guys, this isn't good enough. And we recommended using anonymous credentials. And a really cool outcome of this is that it opened a dialogue with the team behind this digital identity wallet to talk about how to do this in a privacy preserving way. So you can imagine that it's very important to protect anonymous credentials because we want to use them in like actual real applications. And so if we consider our scenario from before of, what if somebody gets a hold of your key, what if someone gets a hold of your secret? Well, if an adversary gets a hold of your credential, they can pose as you. Whatever you have access to, this adversary can have access to. And even worse is actually if this adversary gets a hold of the authorities' keys, now they can make whatever credential they want. I can pretend to be the president, I can pretend to be the provost, and with this key, I can even make nonsensical credentials, such as saying I'm a cat who lives at your house. There's nothing that stops an adversary holding this issuer key to issue weird credentials. And so I've also worked at the intersection of anonymous credentials and threshold cryptography, distributing these and reducing the single point of failure. So I've worked on both issuing this credential, so protecting the authorities key, and distributing the credential itself so that you don't have to store it on a single device, and you can jointly prove that you have this credential without ever reconstructing one place. And so I'm going to do a little tiny peek into this work on distributing the issuer's key. We did it specifically for a signature scheme called BBS, BBS Plus. And this is what the algorithm looks like. And you might notice something that looks familiar. Well, the main difficulty in this work was producing this inversion of this secret key. And so we applied similar techniques that we used for threshold eCDSA into the setting. And we were able to produce a very efficient protocol, two-party, like on the order of milliseconds for two parties, roughly 3 milliseconds, which if you want to compute a BBS Plus signature, just a single party, it's around 1 millisecond. So pretty efficient. And if we revisit, oh yes.
Can you give any intuition for why there's this big discrete jump between 12 and 13?
Yes. So this actually is those boxes are the WAN setting, and so that goes from when we have data centers that are somewhat close together to now we have to go across the world. And so actually that is a pretty good indicator of latency is what is the main bottleneck. Yeah, good question. And if we revisit this picture of my works in the wild, I've actually already had this distributed threshold BBS Plus protocol implemented by a third source person. So, woohoo. And that's the main, of my works. And the question now is, where do we go from here? Well, in the space of digital credentials, we're at the beginning of deploying these digital identities. And something really cool is that this cryptographer's feedback document that we published back last summer started conversations with standard organizations and government people in the US and Canada. And so now we are meeting I am meeting very regularly to discuss directions for how do we do this in North America. Yeah, that map. And for digital credentials, there are many interesting research problems still left to solve, like revocation. If you shouldn't have your driver's license anymore, then it's very important to be able to revoke it. Pseudonyms, and maybe there's hardware and connectivity constraints for when you want to do it at such a large scale. There's also, I'm interested in blind signatures, which are a type of signature where it's another privacy preserving scheme where I can receive a signature on a message that I'm not going to reveal the contents of this message to a signer. And this is very useful, and it's used in privacy preserving internet relay systems like Privacy Pass, which is used by Cloudflare, iCloud relay system. There's a sense deprecated Google One VPN, and the Google Chrome's private state token, I think. And there's parallels to blind signatures with my work on threshold signatures. And so I'm interested in exploring this direction of can we use similar techniques to construct very more efficient blind variants of these deployed signatures. And I briefly touched on this kind of at the very, very beginning. I'm also interested in some foundational questions. So far, we've been talking about signatures for concrete tasks, but they're also fundamental for use in larger protocols, such as those of distributed computing. You can think like Byzantine agreement or broadcasts. Using some sort of authentication of these messages is vital. And so one of my recent works models signatures in the context of these higher level protocols. And I'm interested in, can we expand these ideas to how to model more other advanced types of authentication? And this is the conclusion of the technical portion of the talk. So let's wind down with some fun, non-technical things. You may have noticed some drawings throughout the presentation, such as my very bad North America. I will confess that I do like drawing, and I do like doodling fun little crypto related jokes, funny moments from talks. Like we have the discrete logarithm, and then for the cryptographers, gate by gate gobbling. And then for the very niche cryptographers, a comic about needing forks for a dinner party and having to run a 2 special sound sigma protocol to get a fork. I don't know how many papers that requires you to read to get it, but yeah, I generally like having a good time, and I think maybe that's acknowledged by the community because I was invited to co-chair the RUMP session at Crypto last year. RUMP session, for those who are not familiar, is just like a little session for lightning talks. So, can be fun, they can be serious, and we decided to have a lot of fun with it. And so I dressed up as an adversary and we performed what we called a me in the middle attack, where we annotated all of the serious talks to make them more goofy. And a fun little tidbit about being an adversary at the flagship crypto conference is that around this time I was invited to be on the research ethics committee for SMP, which the irony is not lost on me, and I love it. But yeah, I mean, apart from me having a good time, I genuinely want everyone else to have a good time around me. I just, I want everyone else to have a great time. And so even throughout my undergrad and grad experiences, I've been very involved in my community. Back in undergrad, I got to serve on my CS department student advisory board, and I even helped find a solution for a rule that was affecting an underrepresented group that they had raised the issue with me, which I'm really proud of. And back in grad school, I helped design this lab space for my lab, even though I was going to graduate before I moved, because I want them to have a nice space where they are happy. And so, yeah, and in terms of teaching and mentoring between undergrad and grad, I did a Girls Who Code summer program, and that was kind of where I discovered how much I love mentoring and teaching. And it's something that I really hope to continue helping students discover their passions. And this is all an elaborate ploy to make people look at pictures of my cats. You guys fell for it. My adversary, Gertrude. There's only 2 cats. I just but there's more than 2 photos of them. Yeah, my adversary Gertrude actually has deleted proofs before deadlines, and I'm just like, oh my gosh, and she would do it again in a heartbeat. But yes, that's my talk.
Okay, thank you so much. Any questions?
Zoom folks, if you have questions, feel free to unmute and ask, since we're not too large a group, or you can also type it in the chat and we'll ask it for you, or you can raise your hand virtually, or Zoom, but Zoom hand or real hand, and we can call on you.
Too many options, Rebecca.
Go ahead.
That may portray how little of the math I understood despite really trying, which is also not your fault. So with your what you talked about the most with the key distribution, like splitting up to the private key, what happens? So in the case an adversary, I understand that they can't decrypt the message unless they reach the threshold, but can they disrupt the encryption of the method if they have less than the threshold?
As in, like, is the question like, can I block something from happening? Like, I want
Yeah.
to, yeah, so it is, it depends on like what your corruption threshold is. So if you have like enough shares of something and like few enough adversaries you consider, then you kind of like have enough backup that like, oh, even if you try to mess with it, like I can still get it anyway. But if you have it where there's like not enough like leeway between honest parties and like potential adversaries, then there's actually nothing you can do. Like there are impossibility results. You can kind of think about it as like, if I don't have enough redundancy, then like, how do I know who's telling the truth and who's lying?
Okay, and then what if the node goes offline? Is it kind of the same thing where like you come up with that?
Yeah. So we kind of consider that as like, oh, maybe the adversary turned it off. So
Mhm.